Welcome to the next video in the group theory series. Here you can see an overview of everything that we'll be discussing in this video. In this video, we will introduce a geometric example of a group. Start by drawing an equilateral triangle and label its vertices ABC counterclockwise around the triangle. And we will write down all of the symmetries of this triangle. The first is going to be a rotation by 120 degrees, which sends A to B, B to C, and C to A. We will denote this rotation by an R. If we perform this rotation a second time, or from the start do a 240-degree rotation, this sends A to C, B to A, C to B. We will denote this rotation by R squared. If we keep going, then we get R cubed, a rotation by 360 degrees. This is equivalent to a 0-degree rotation. We will denote this by either an R to the 0 or simply the numeral 1. It is likely no surprise that this will eventually serve as an identity element, but that will have to wait. We've exhausted the rotations, but there are more symmetries. Let's not forget the reflections. If we draw an axis of symmetry through the vertex A and the midpoint of the segment BC, then the reflection about this axis is another symmetry which we can denote by S sub A. We can likewise get reflections SB, SC through axes containing B and C respectively. We are now in a position to write our set of objects. D sub 6 is the set of 1R R squared SA SB SC. We next turn this set into a group by equipping it with an operation. It may help to realize that a symmetry is a function, sigma, from R squared to R squared. Therefore, it is possible to compose symmetries. We will take it for granted that the composition of symmetries is a symmetry. And as we've seen elsewhere, associativity always holds for the operation of composition of functions. We should note that the identity symmetry 1, which leaves every point fixed, acts as an identity with composition, which means that sigma compose 1 is 1 compose sigma is just sigma for every sigma in D6. Finally, we should note that each symmetry has an inverse. It's best to see this by directly identifying each inverse, since these will be useful in future calculations. So Doing a single rotation followed by a double rotation gets you back to the identity. So r times r squared is equal to 1, meaning that r and r squared are inverses of each other, right? So the inverse of r is r squared, and the inverse of r squared is r. You could also flip this around and still make the same argument. Any reflection is going to be its own inverse, because if you reflect and then do that same reflection again, you're back to where you started. So SA is its own inverse, and likewise for the other reflections. It's also fairly straightforward that no matter what group you're in, the identity element is always its own inverse. Now, let's go ahead and think about taking the product of R and SA. You can follow the calculations over here in this page to see that R times SA is SC. Similarly, you can see that R times or R squared times SA is SB, and therefore we don't really need these other symbols SB and SC, because we could merely write SB as R squared S, and we could merely write SC as RS. And so, in some sense, just as kind of cutting down on the number of symbols, we can really just pick any one reflection. And the choice of SA was arbitrary, so it really doesn't matter which reflection we choose to be our reflection. We pick any one arbitrarily and then write down all the other reflections as R times S and R squared times S. This is a simpler representation of D6. It also makes clear that in some sense, R and S generate all of the other elements in D6.